ultraviolet spectroscopy. Determination of dissociation energy from dissociation limit. Let us consider an electronic excitation of a molecule AB which can lead to dissociation when a transition from the ground state of AB to a stable excited state of AB star exceeds the dissociation limit as shown in the figures below. So we have the ground state AB here, and we have the excited state AB there. Okay. We have the energy of excitation, dissociation energy of the ground state, and the dissociation energy of the excited state. A very good example is iodine. Here we will have iodine in the ground state, the iodine in the excited state. So we move from I2 to I plus I, and then we can move to I plus I star. Determination of dissociation energy. Here D prime E gives the dissociation energy of the excited state representing the process AB going to A plus B star. And D double prime 0 gives the dissociation energy of the ground state, the normal dissociation energy, representing this process AB to A plus B. The dissociation limit measures the energy transition represented by D double prime O plus EX, where EX is the excitation energy of the atom B, which can be obtained from atomic spectral data. Hence, D double prime 0 can be determined from dissociation limit and EX. Here's an example. The dissociation limit for iodine vapor is observed at 499.5 nanometers. Given that the excitation energy of the iodine atom is 90.7 kilojoules per mole, determine the dissociation energy of iodine. Let's look at the solution now. The energy corresponding to 499.5 nanometers is given by E is equal to Na, Avogadro's number, times H times C over lambda. So E is equal to NaHC over lambda, and if we substitute with the values, we obtain that E is actually equal to 239.5 kilojoules per mole. This is the energy needed for the process I2 to I star, then I star to I plus I star. That is, E is equal to 39.5 kilojoules per mole. Now for the process I to I star, E is 90.7 kilojoules per mole. Subtracting gives I2 to I plus I, and the energy will be 148.8 kilojoules per mole. This is the normal dissociation energy for iodine. Dissociation energies from vibrational-electronic spectra. The most common electronic transitions are those given by A and B above, in which no continuum is observed. Instead, the limit is calculated assuming that at the limit, the separation between the successive vibrational energy levels is 0, implying that the limit, the anharmonicity equation is equal to 0. Okay, calculation of D naught energy is continued. Energy in wave numbers omega V is equal to E over HC, which is equal to V plus a half into nu bar E minus V plus a half all squared XE nu bar E. And this should be equal to naught, meaning that omega V is equal to nu bar E into 1 minus 2 XE into Vmax plus 1, close, and that should be equal to 0. That's equation 2. On the sorting out the algebra, Vmax becomes 1 over 2xe, or minus 1. If we substitute Vmax into equation 2, we obtain energy corresponding to the dissociation energy. Now, where do these electronic transitions come from? Absorption of a photon usually is from excitation of electrons belonging to a small group of atoms, e.g., the carbonyl group. For example, carbonyl group absorbs at 290 per nanometer, 290 nanometers wavelength. Groups with characteristic absorptions are called chromophores. Their presence accounts for the color of the substance they belong to. Let's look at the specific transitions. Charge transfer from a ligand to d orbitals of the central atom in a d metal complex, or vice versa. Example, the permanganate ion MnO4-, where charge distribution accompanies migration of an electron from oxygen to manganese atom, accounts for its intense violet color. Absorption is in 420 to 700 nanometer. Specific transitions. In the carbonyl compound, one electron from the lone pair on oxygen is excited into an empty pi star orbital of the carbonyl group, giving rise to N to pi star transition. Energy involved is in the range of 4 electron volts, where 1 electron volt is about 8,000 per centimeter. The carbon-carbon double bond is a chromophore when absorption of 1 photon excites 1 pi electron into the pi star antibonding orbital, giving rise to a pi to pi star transition. Here the energy is 7 electron volts. In conjugated double bonds, absorption at 180 nanometers, i.e. in UV. On conjugation of double bond, molecular orbitals' energies lie closer together. Hence, transitions shift into visible region of spectrum. Examples are the many reds and yellows of vegetation and flowers. A very important pi to pi star transition is in the photochemical mechanism of vision, involving the proton rhodopsin in the retina in the combination with 1,1-cis-retinol, which acts as a chromophore and hence a receptor of photons entering the eye at 380 nanometers. In combination with the protein, absorption shifts to 500 nanometers because of conjugation, can absorb over the entire visible region. In its electronically excited state, the conjugated chain can isomerize to a trans-retinol, a longer different shape, not fitting into the protein.